Hi everyone, I am Anna Bensel, and I built my case study in finance for CSCI 89 deep learning to basically test the question that comes up in a lot of financial machine learning, which does a more complex model actually give you a better risk forecast. This actually grew out of a finance course I took last semester with Dr. Iwata. If you're a Harvard student, it's CSCI 278, Applied Quantitative Finance in Machine Learning. And I wanted a project I could actually eventually bring to a risk desk or a trader, not just something that kind of lives in a notebook. But this is not an institutional grade project. This is just kind of my jumping off point to better understand kind of everything with that. So um, I'm starting with my problem, which a systems forecast analyzes realized volatility over 1, 5, and 10 days, and the separate estimates of the probability of a severe 5-day downside move. So I built it around three connected instruments: ES Futures, which trades almost around the clock; SPY, which is a liquid equity proxy; and VIX, which summarizes what options traders expect volatility to be. The goal is risk awareness for a trader or risk desk, not necessarily predicting the direction of any stock market moves or any market moves. So I went with three hypotheses, and two of them did not hold up, which turned out to be the most interesting part actually of this project. I expected the sequences to beat a dense network, and I expected VIX features to help the most stressed markets, and expected the tail risk task to improve the shared representation. So to judge the results fairly, I required basically more than a good rock. I also required a usable prediction and recall for the rare events, since rock can look deceptively strong when positives are scarce. So for the data, I actually did not download any data sets. Everything is from Y Finance or Yahoo Finance. You can get directly into a Jupyter notebook. And I started from January 2010, so after the 2008 market crash, just using ESP, SPY, and VIX. After aligning all of the three, I actually built rolling features and forward-looking targets. And the final sample was 3,906 total observations. And I use continuous feature series for basically reproducibility, which means I avoid treating the raw ES price as a stable input, because everything downstream is built from returns and ranges instead, to basically sidestep roll adjustment discontinuities. So going into my features, I had 39 features across 6 different groups: returns, volatility, trends and stress, range and volume together, options derived, and cross market. One worth calling out though is the volatility risk premium, because I have it as VIX minus the 20-day realized SPY volatility. And so a positive value means options traders are pricing in more volatility than the market has actually shown, which is not necessarily a predictor of a crash, but it's showing kind of this risk appetite. So I'm going to break down the full pipeline. Raw data became 39 features organized into 40-day sequences and fed identically into 4 architectures: the dense, the LSTM, TCN, and transformers, each producing a volatility forecast and a tail risk probability. It was the same input for every model, which is kind of what makes this comparison the most fair it can be. ESP and SPY track almost on top of each other, as you can see in this chart, since 2010. There are gaps from financing, dividends, and contract constructions, and I chose to keep both because ES can react to overnight news before SPY cash session opens. So it's real and non-redundant information, even though it has a 0.97 correlation. So I did feel like that was important to keep in. For VIX and realized volatility, they move together during real stress but separate during calm periods, since options price carries a risk premium and their rolling correlation actually swaps leadership over time. So sometimes VIX predicts better and sometimes recent realized vol does. The instability is exactly why I chose to use a chronological split instead of a random one, because a random one would blend all the regimes together and would make the evaluation look more stable than a real deployment basically ever would. So a few numbers from this matrix. ES and SPY returns correlate, like I've mentioned before, 0.97. VIX correlates 0.72 with the 5-day target, which is actually pretty genuinely strong. The volatility risk premium only correlates negative 0.1, so it's weak on its own. But the overlap is meant for a bigger model risked spending capacity, rederiving information I'd already handed to it directly, which matters because it actually matters a lot once we get to the results. So I'll keep that to myself for now. Then we have the chronological split, which is 65, 15, and 20, time ordered with 2,499 trainings, 586 validation, and 782 test sequences, each 40 days by the 39 features. So I fit both scalars into training data only, so the high volatility test periods can't leak into how the model normalizes the inputs. I know I've kind of mentioned the architecture, so I'm going to jump into those. All sharing identical outputs. It compares and isolates the architecture alone. With Dense, we have 442,000 parameters, the largest simply from flattening the input. LSTM with 140,000, TCN with 37,000, and Transformer with 76,000. Each model trains on a shared loss. So MSE on volatility plus 0.5 times cross entropy on tail risk downweighed because that label is rare and it's noisy. Atom Optimizer was up to 50 epochs with early stopping on a CPU. Just to also be clear, I was having trouble with Google Colab Pro and getting GPU and TPU working. So it worked with the CPU and it did fine. If you were trying to reproduce this, I would highly encourage doing at the full 50 with no early stopping. It might be a bit noisy and it might have some overfitting, which was the genuine fear for a while, but regardless. On validation, LSTM has the lowest error, bottoming out around epoch 6. So with Dense being actually pretty close behind that. TCN and Transformer started overfitting almost immediately. So like I mentioned before, there was concerns with overfitting, but regardless, if I had stopped there, I'd be telling you basically LSTM is the clear winner, but keep that in mind. I'm going to keep it, hold on, the next slide changes that story. On the held out test set, Dense wins on like every horizon. 5-day results, the MAE of 4.885, correlation of 0.583, and the R squared of 0.117. So positive but modest. And I wouldn't call this highly accurate. My best true explanation is that the engineered features already encode a lot of the temporal history directly. So flattening gave Dense a shortcut, and the sequence models had to learn the hard way. But the real point of this was the validation and test rankings disagreed. So LSTM looked the strongest before the holdout period, and Dense generalized better after it. So the disagreement is exactly the failure mode chronological evaluation that is designed to catch, and it's the most single important takeaway, in my opinion, for that I figured out from this project. So every model compresses the biggest volatility spike towards the center. None really fully catch it. Dense tracks routine periods closely, which is why its average error looks so good, while LSTM reacts more sharply during the actual stress, despite a worse overall number. Dense's advantage narrows kind of right when the volatility spikes. So that's kind of a reminder that, like, for me looking at this, that the best average model isn't necessarily the safest one when risk trading. So this was the weakest part of the system. Transformer had the best ROC, which was 0.752. So good at ranking risky trade days before the safe ones, but Dense had the best PR-OC, which was the only model to predict any positive case at the default threshold. So LSTM and Transformer's probabilities never crossed it. So a model can rank rare events pretty well, actually, and still fall completely as a usable classifier if the threshold doesn't match how rare the event is, which feels like a pretty good, like, idea of like what imbalance is. So I split this like test period into 4 regimes: SPY, momentum, and volatility level. Dense wins both bullish regimes. LSTM wins both bearish regimes, including like the bear slash high volatility, and the one that matters most for risk trading management. So this is exactly why LSTM looks strong in validation, and that the window happened to favor it. So kind of translating that into dollar risk, everything that I've just talked about, taking Dense's final forecast, which is 11.5 annualized volatility, I converted that into a 5-day dollar move, which would be about $6,090 per ES contract, or 609 for a micro. This isn't a trading signal or stop loss. It's just translating a statistical forecast into a scale that means something to a trader, and kind of illustrates why micro contracts exist. I mean, just the threshold itself is completely different. So the headline for me here isn't that like dense one, right? It's that the validation and test rankings disagreed, which is why, which is, I guess, exactly what chronological evaluation exists to catch. Limitations would be no persistence or hard baseline yet, continuous feature role effects, overlapping targets, and only the 21 points in the bear low regime. The bottom line is dense was best overall. LSTM captures the best in bearish regimes. Transformers are best for like tail risk ranking and more complexity, but didn't automatically mean a better model. If I were to go like next step would be probably a regime aware dense LSTM ensemble with proper baselines. And I've actually like used a little bit of this alongside in my CSCI89B project for natural language processing. And then I also kind of used this exact same thing. This is just like an actual how I use this project to help pass a prop from evaluation challenge, which was kind of my real world check on how useful this could be. I really enjoyed this class, and thank you guys so much for taking a look at my project.